In the last, I guess, mini unit, we talked about the chain rule and how we can use the chain rule with functions inside functions. And probably one of the most direct applications is implicit differentiation. So what do I mean by implicit differentiation? Alright, so we've been looking at something, we've been doing derivatives with functions that are called explicit functions. Explicit. Which means basically y is equal to f of x, or y is equal to a function that just can only be described in x. What implicit basically describes is that the y can actually appear anywhere, and it doesn't just have to be solely y. It could be like y squared or even like 3y cubed. So it might be, here's an example that makes sense. This is not an implicit equation because it's described in both y and x's. And we're going to be looking at the derivatives of these types of, I guess, equations and see how the chain rule ties in quite nicely with implicit differentiation. So let's just continue with some examples for implicit, right? So this is an example of an implicit function. See that it's defined both in terms of x's and y's. And in some cases we can actually solve for y and turn it into an explicit function. And in some cases we can't, like this one I just gave, right? How do you even solve for y? Because it's a squared and a regular term. So that's why we have to talk about implicit differentiation. And then let's do some examples. So we'll be right back. Okay, so we're going to look at this example. Have y squared equals x. We are asked, what is dy dx? So we could kind of use the chain rule this way. So what the main idea of implicit differentiation is that we need to treat y as a function of x. In other words, if we were to take the derivative of both sides, there we go. We need to treat y as a function of x. Simply what we do is we take the derivative of this with respect to x and then apply the chain rule. So we want to take the derivative, so look at this, let's see, of the outside, which is the squared function, so 2y, right? And then we want to multiply by the derivative of the inside, which is y. So what is the derivative of y? We don't know. So we're going to write it as the derivative of y with respect to x. And then similarly, we're going to use just a regular power rule here, so you get this. And then the next step is simply just to solve for dy dx. So dy dx is equal to 1 over 2y. And this is what the derivative is. As you can see, it is kind of like the chain rule in disguise, because y is a function of x. So what we do is do the outside, and then we multiply by the chain, right? The inside, which is y. Another way to think about this is every time you differentiate y, you always want to tack on this term, the dy dx. So we're going to look at another example just to get used to this process. Example 2, find the slope of x squared plus y squared equals 25. So at the point 3, 4, so if you think about this equation, this is just describes an equation of a circle. So let me just draw a poor circle here, and then we have to estimate where it is. So maybe like here, right? We see that the slope is probably like some type of positive slope if we were to plot this on an xy plane, right? And I were to plot, let's see, 1, 2, 3 right here, 1, 2, 3, 4, right? Maybe it'll be right there. So we know, based on this drawing, it has to be a positive slope. So that's a good double check method, is to try to visualize the graph and where the point is. And when we're thinking about slope, we want to find specifically what is the derivative of y with respect to x, or otherwise known as the rise over the run, right? This is slope. The rise is the y, and the run is the x. So in order to do that, we have to take the derivative with respect to x of both sides of the equation, right? We kind of like do the algebra rule of whatever you do on one side, you have to do to the other. And then we see these are just a sum, so I'm going to treat them separately. 2x plus, and then I'm going to write it like this just to show you the implicit part, is equal to 0, right? The 2x we already found the derivative of. This one we have to use the chain rule. And remember, kind of it looks like last example, so we want to take the derivative of the outside, right? Keep the inside the same, which is y, and then tack on the chain, which is dy dx, and it's equal to 0. Our next step is to simply solve for dy. Right, so in order to do that, I need to move this over and then divide by this, right? So move it over, this becomes negative 2x, and divide by 2y, right? Since these are multiplied together. And then I can just simplify through, and I get dy dx is defined to be negative x over y. In other words, the formula to find the slope at any point you want is given by this equation. So let's actually plug in 3, negative 4 in here and see what we get. So if I were to, I'll just bring it here, dy dx is equal to negative x, which is 3, divided by y, which is negative 4. In other words, the slope is 3/4. So again, we see how to use implicit differentiation. We just have to remember it's kind of like the chain rule in disguise. So let's keep going with some more examples. Okay, so very similar to the last problem, we want to differentiate this, find dy dx at a point given to us here, right? So the first step is always to do the derivative of both sides with respect to x. And since y is a function of x, we have to look at that specifically. So we know this is an implicit differentiation problem. So let me just do this one since it's really easy. It's 0, and then we look at this, right? Let me do this here. So we have the first one, which is 2x, right? Minus, and this is where it gets kind of tricky because y is a function of x, so you have to pretend y is kind of like x in this case. So you have a function of x multiplied by another function of x. That means we have to use the product rule. So let's try that. So let me do it off to the side here. So if x is the first one and y is our second one, if we differentiate the first, we get 1, and if we differentiate dy, well, it'll be, if you want to really use the chain rule, it would be this. This hops down here, this becomes 1, that becomes 0, but then we have to tack on a dy dx. In other words, just dy dx. Let me write it here actually. Dy dx. I wrote the functions here and then the derivatives below. We just want to fit it into the product rule formula, which is given by this. So let's actually fit this. So it's the derivative of f, keep g the same, so it's just y. And then f, keep this, differentiate that, so you want these two now. So it's plus x dy dx, right? And then we've seen this before, we've done this in the previous two examples. It's just 2y and then you tack on the chain, which is equal to 0. So now we want to begin trying to solve this. Actually, I made a mistake here. It should actually be like this. Now you want to just start simplifying and solving for dy, and this is more of a typical problem. You'll see a couple terms of dy dx, and you have to solve for it. So let me just simplify this through. Right? Oops, not equal to 0. There we go. So let's see. We want to get all dy, any term without dy dx on the other side of the equation, meaning this one and this one, right? So then we would get, if I move it to the right side, I get this, right? Keeping this the same. And then we move it to the right side, so I get y minus 2x, right? Let me just scroll down here because we need some more space. There we go. Now we want to see that, notice that these have common factors, and that is specifically dy dx. So we want to factor that out, and we're left with negative x plus 2y is equal to y minus 2x, and then we can finally solve for dy dx by dividing both sides by negative x plus 2y. In other words, dy dx is equal to y minus 2x divided by negative x plus 2y. And this is the formula for the derivative. Now we want to plug in the point. What did I say as the point? We want it to be negative 1, 2, right? So we want to evaluate at -1, 2, and we just start plugging in 2 minus 2 times -1 divided by, we have negative of -1 plus 2 times 2, and then we get what? 2 plus 2, and then 1 plus 4, which is equal to 4 divided by 5. And this is our slope at that point with an implicit function. So let me zoom out here. Right? This is our implicit function here. So we wanted to take the derivative with respect to x on both sides and apply the chain rule here, right here. And then this one's kind of a mix of a chain rule, right, with this, I guess, second term in a way, and the product rule here, this middle term. And then so we simplify through, and then we want to solve for dy dx, so we have to get all terms that are not dy dx on the other side, so we can factor out a dy dx on the left side. And then from there we can just divide what's the factored form to get dy dx, right? So as you can see, it's just a direct application of the chain rule. So hopefully next time we're going to look at more examples of implicit differentiation in more harder contexts. So that's it for this video.